This lesson is the actual fun one of the course. We're going to work examples using real data in an actual interactive worksheet. The goal is to learn how to use the campaign worksheets, both planning and evaluation, by working through some examples. Before we can do that, we need to know how to start. There are two ways to start the worksheet. One is either to use the web URL, which is the easy way, or for those already experienced with R and RStudio, you can download the source code and run it yourself. The web URL is the following, and this is supplied here and in a number of places in this course. To use the RStudio version, you need, of course, to have both R and RStudio installed. Once you have that, you'll want to use R commands to install and make sure you've loaded the Shiny package. Once you have that, you bring the source code to your machine. Here I've shown how to do it at the command line on Apple OS X using the git clone command. But you can also navigate to that URL and download all the source code as a zip file or other ways from Git. Once you have all the source code downloaded, you then need to open the campaignplanner.r project file. Here I've shown how to do it at the command line with the open command on Mac OS X. However, you can also open this file by navigating to it with RStudio or sometimes by clicking on it with the File Explorer. Once you've opened the project, open the file ui.r, and then in the file browser of ui.r, you will now see a Run App button. Pressing this button will now run the application. For this demonstration, we're going to do things the easy way and just click on this URL. For the first example, we'll use the campaign evaluation sheet. The sheet looks complicated, but there are really only a couple controls. The first one is the sheet chooser, which moves the sheet from evaluation and planning mode. The second control is where you type in your example results that you wish to have analyzed. The third control is the extra analysis controls, where you specify additional things you'd like done during your analysis. All of the rest of the sheet is a table and a graph, which are basically results of the analysis. These guides will be supplied as part of the course extras. Here, we've started the analysis worksheet. We'll move it from planning mode to evaluate mode, which is often how things are in reality, that we need to evaluate campaigns that have already been run. I'm going to type in one of my favorite example campaigns. It is a campaign where we tried 100 actions, we had one success, and we value any success at $2 each. In the second campaign, we had 2 successes, and we value any success at $1. We'll leave the extra analysis controls alone. Now that we've set that, the rest of the sheet is populated. First, we have a table, which largely copies in what we've typed, the number of actions, the number of successes, and the valuation of any success. It also has the observed success rates and observed values per action. Notice that the observed success rates are not the ideal values 1% and 2% that we typed in, but 1.5% and 2.5%. This is because all analysis on this sheet is done in a Bayesian method using something called an uninformative Jeffreys prior. The uninformative prior is similar to seeding the result with a little initial data before performing the analysis. The math can be hard, but it solves a number of technical problems during Bayesian analysis. The overall effect is, since we are analyzing campaigns that have success rates very much below a half, the Jeffreys prior looks like a slight upward bias on all results. Where we had a campaign that had 1% conversion rate, we estimate 1.5. This effect goes away as the number of successes gets large, say 10. This bias is also much smaller than any of the error bars that also interfere with analysis, so it will not be a problem going forward. However, you do want to know, for very rare, high-valued campaigns, you don't want to pursue those campaigns due to any illusion called by this Jeffreys prior. That being said, the table data is also copied in more detail into the graph. Campaign 1 is the solid red line. Its mean is shown with a thin vertical line. Campaign 2 is the dashed blue line, and its mean is shown with the blue line, vertical. The x-axis are possible values of the population we have observed. The experiment is we've sent out a number of envelopes and received a number of successes. What we don't know are the true response rates for each of these 2 different populations we sent to. This graph is called the posterior graph, and for every possible value of the value per action of these unknown populations, it says how likely is that given our data. And basically, the most likely values are these values near 2.5 cents per action, and both campaigns have mass that's spread out quite wide. We haven't run enough experiments to get much certainty of that estimate. We don't see these distributions being stacked up near the mean like we'd like in a very good result. Also, the wish price is one of our additional analysis controls. That controls the location of this black dashed line. Right now it's set at a nickel per action, which is much higher than the observed rates of 2 to 2.5 cents per action we're estimating on these campaigns. What is done is for each campaign we calculate how much of the probability mass, which is shown shaded here, is above the wish line. The first campaign may have as much as 17% of its mass, or a 17% probability of actually having come from a population that's worth a nickel or more, whereas the second campaign may only have a 7% chance of having come from such a population. The idea is the second campaign is less consistent with a nickel population. In fact, neither campaign is very consistent with a population worth a nickel, as they both showed values much near 2 to 2.5 cents. Finally, we have the decision of which campaign is likely more valuable given our evidence. It says, given our evidence, campaign 1 has a 53% chance of being more valuable than campaign 2. Obviously, that is very near a half, so this is a very equivocal or unuseful result. In fact, most of the results on this table are equivocal. This is a symptom of having run too small an experiment. Sending out 100 actions to each campaign was far too few. Suppose instead we had sent out 1,000. We can simulate that by upping the scale factor. Now, the campaigns are actually 10 times as big. So when we sent out 100 actions, we recorded as 1,000. When we recorded one success, we record it down here as 10. So this is a new result that we don't quite have yet, that if we'd run a 10 times larger campaign and things had come out exactly in the ratios we saw before, what would that experiment look like? What we see is the distributions are getting much tighter. The possible values for the population intensities, the facts we don't know but are trying to estimate from these samples, are now concentrated with means much closer to the observed values of 2 cents. And the width of these distributions, which is essentially going to drive variance, and what our entire purpose is to drive variance down, or variance on uncertainty, want to drive them both down, this variance width is now much smaller. Another type of campaign result that shows a lot of possible problems with this sort of analysis is what I call the unsatisfactory campaign. So if the second campaign was actually at a much higher price point, so we sent out 100 invitations to buy at $2 each, and 100 more invitations to buy at $25 each. And the first set of invitations had 2 successes, and the second set of invitations had none. So basically, nobody in our sample population was willing to buy the product at $25. What would we have learned? We see the campaigns are much more confused. The 2 mean lines are very close to each other. We saw 2 successes on campaign 1 and 0 on campaign 2. And actually, you see the blue mean is to the right of the red mean, that the system thinks possibly the campaign that never had a success could still be the more valuable one because of the very attractive high price it hasn't yet gotten from any campaign. And a lot of uncertainty of the relative value of the campaigns, it thinks there's a 53% chance the second campaign could be the more valuable one. Again, this is all symptoms of not having enough data. And as you see, by controlling the size of the data, we're starting to move out of mere evaluation into the realm of planning. So for our next few examples, we're going to move to the planning worksheet. The planning worksheet works similarly to the valuation worksheet. The user, instead of supplying the counts that came from an actual pair of campaigns, supplies a notional description of possible campaigns. They supply the value per success, which they may know, and they're asked to supply a guess at the population's unknown true response rate. This is a notional value. We don't think they really believe this rate, but it's a rate they're interested in testing. There's again a set of extra analysis controls, and then a graph that presents the results of the plan analysis. After that graph, there is a copy of what looks a lot like the evaluation campaign. Just to help educate the user, by pressing the regenerate button, we can draw over and over again experiments that would have resulted if the population had been as described. This helps you tell whether you've got a setup or a sample size that's big enough or not. We're now on the planning worksheet, where you enter descriptions of 2 theoretical campaigns, the success rate of each campaign and the value of success. Let's enter a campaign very similar to one of the ones we've already analyzed the results of. So that would be a campaign with a 1% success rate and a success valuation of $2 per success, and a second campaign with a 2% success rate and a success valuation of $1 per success. We'll ignore the additional controls for a bit, and we'll go to the first part of the results. This is the size suggestion table. The 3 result columns in the size suggestion table are as follows. The actions to meet error goals is, if you were to run each campaign with a number of actions equal to the suggested numbers, then with probability 1 minus the error probability, so with 95% probability, we would measure each campaign to within plus or minus 20% of its true value. It's actually plus or minus 20% of the largest campaign, so smaller ones are off by the same absolute error, which might be a slightly larger relative error. As you see, these counts are fairly large to achieve that. We need about 7,500 actions in the first campaign to measure within 20% relative pricing or value error with 95% certainty, and about 3,800 actions on the second campaign. The issue is the rarer campaign needs more clicks both to see a given number of actions and has a higher initial variance because of the higher success value per success, and we want to cut that variance. Because the actions to meet error goals, which is the thing in this system that is closest to traditional power and significance test design, is often too expensive, we also supply the actions to meet count goals. Count goal is entered here. It can be 5 or 10. 10 is probably a very good number. And it just takes your success rate and divides through to figure out how many actions it would have to do at the given success rate to expect 10 successes. And you see these numbers are smaller, 1,000 and 500. We can enter those. So we'll run the first campaign for 1,000 actions and the second for 500, and that populates the result table. Here we see the 2 curves, the dashed blue and solid red, are overlaid, that both campaigns have very similar distributions. In this case, the x-axis is the expected number of successes seen in an actual trial divided by the action size. And so we basically expect these campaigns to see about the same value, which is how they've been chosen. And it also says that we expect to see judge one campaign larger than the other about 45% of the time one way and 45% of the time the other way. Again, these are identical campaigns, so that's sensible. In fact, the only difference between this and 50% is sometimes both of these campaigns have identical success counts, so neither is strictly greater than the other. The fun thing we can do is we can run this experimental design, which is the actual chosen values of the unknown true intensities and values and the size counts, and we can generate what does a typical output look like. And a typical output is, with 1,000 actions on the first campaign, we might see 7 successes, and with 500 actions on the second campaign, we might see 16 successes. And we see the mean for the solid campaign 1 is to the left of the mean for the dashed campaign 2. So someone would perceive campaign 1 as being worth less than campaign 2 in this experiment. Regenerate generates another experiment, another, and here we see they've switched roles. This time they would have perceived the campaign 1, the solid campaign, as being more valuable than the other. And that's what these percentages are talking about, is who's ordered where, typically in the outcomes. This plan is probably a little small. If we actually were to enter something near the proper actions to error goals plan size, which are much larger, we get much tighter distributions, but much less often do the observations differ by a significant number of dollars. Business people really don't care if they pick a campaign that is nearly the best one. They basically would want to stop their so-called sensing phase, where they're running traffic on both campaigns, and just settle on one campaign and go, and perhaps use their testing infrastructure for another project. We've sort of been looking at a negative or null case for this sort of testing. Let's actually look at a pair of campaigns where we're positing they may actually have different expected values. Let's make the first campaign convert at a 1% rate, and the second campaign convert at a 1.2% rate, both with the same per success value. Then the planning sheet says a good plan is to put about 5,000 actions on each campaign. We're going to use that instead of the lesser actions to meet count goals. We're going to try to get a nice clean measurement of the value of each campaign. We now see that In the planning sheet, these plots, which are again the plots of the expected experiment values, so this is the number of successes seen in each experiment divided by the size of the experiment, the experiment value humps are starting to separate, that we expect to see one campaign and the same campaign come out higher most of the time. And it's the second campaign which is in fact worth 20% more than the other. And in fact, we expect to only choose the second campaign 15% of the time. So 85% of the time or 82% of the time, we have a good shot at choosing the right campaign. And when we hit the regenerate button, we see the order is somewhat stable. The dashed guy is often on the correct side, which is the right. So we're seeing that this is probably a good experiment size to order these campaigns that are about 20% apart, and that makes sense because we've insisted that the highest value one be estimated to within about a relative error of 20%. For my final example, I'd like to show you what I call the so-called region of indifference or rate of indifference plan. So suppose through prior knowledge or an initial campaign, we know the value of the first campaign. We know that the populations for our product tend to convert at 1% when we ask them for $2. And then suppose we're trying to test what happens if we ask them for $25. Well, from the suggested campaign's action sizes table, it says to make the same amount of money, and it was a 1% campaign at $2, you only need this 0.08% campaign. So we'll put that number in. The idea is that the ratio between the success values should be 1 over the ratio between the success rates. Then each campaign is developing the same expected value per action, which means if we are paying for these actions, we would be indifferent which campaign to run. So if the success rate of this rare campaign were higher, we would then consider it the more valuable campaign. Let's see if we could even detect that. The experimental design says we have to put a lot of data on that second campaign to get its value to within 20%. We can't afford that, so we're only going to put 10,000 units, which is the actions to meet counts, and then we'll go ahead and put 4,000 on the first campaign. That's almost what it needs to get a good 20% accurate estimate with high probability, and much more than it needs to get a good count estimate. So this experimental design is sort of a compromise. Only the very large companies can routinely run experiments with hundreds of thousands of test subjects. What we're hoping is that the higher value campaign, which is the dashed one, and we can tell that because its success rate is above the specified matching rate where the two are equal, that this campaign that tends to be the right of the red campaign often shows up to the right of the red campaign in experiments. And here it didn't. It showed up on the left. There it showed up on the right. There it showed up on the right. There it showed up on the right. And there it showed up on the left. Every time it shows up on the right, we pick it and we've correctly picked the right campaign. Every time it shows up on the left, when we pick the red one, we've picked the wrong campaign and we lose expected value. And basically, this number here says we should pick campaign 2 as the unique best one about 70% of the time. So we have an error rate of around 30%. And for very rare campaigns, you really have to accept that. There's no substitute to running a larger experiment to get the uncertainty down. The point of the planner and the evaluator is you can see whether you're dealing with rates you're capable of measuring or not before you even try the experiment. What you should now know: how to run and interpret the campaign evaluation worksheet, and how to run the campaign planning worksheet. The evaluation worksheet gives you a tool to discuss uncertainty. It produces graphs of the posterior distribution of the unknown true expected value of your populations. So you can measure what happens in your sample, but that's not necessarily what was true about the population the sample was drawn from. However, the distributions estimate what possible values that true population may have as its value per action. This system is a Bayesian estimate. The planning worksheet is actually simpler. It bullies the user into saying what the exact unknown true values of the population are. So these are questions you really cannot confidently answer. So we suggest you try a few values. Then, given those parameters, it just does the forward simulation. What to take away? You should now have some confidence in working on both the worksheets. And also on the planning worksheet, you should take some joy in pressing the regenerate button again and again. Next lesson, we're going to give a theoretical overview of the justifications of the types of measurements and estimates we used in the previous worksheet.